Follow Shadow Junior Twin.
So today we're going over the searching algorithms, and there's only a couple that we need to know. It's a lot easier than the sorting algorithm, so this video should be quite quick. But this week I'm going to go over the searching algorithms, the sorting algorithms, bigger notation, and trees. So we've got quite a lot to get through this week. But we have 135 days left until paper one, so that's going to be all good. So, as I just mentioned, there's only two searching algorithms we actually need to know. There's quite a few more sorting algorithms, so that longer video is probably going to end up on my YouTube, which is in my bio, but this video shouldn't be that long, so we can just get through this. So we need to know a linear search and a binary search. And a linear search is an intuitive algorithm. You probably think of a linear search when you think of how you would find a target value if you're given an array of values, right? And so let's go over it first and see if you can maybe come up with it before I even go over it, unless you already know it, of course. So, we'll go over a worded definition first. It works by looping through an array, checking each of the indexes to see if it matches the target value. If it does, it can return the index, and otherwise it keeps going through the array looking for this target value in this array. So we're going to go over the pseudocode and a tracing example, so it really is ingrained in your brain, and we're also going to go over some exam questions. But let's first look at the pseudocode. So if you're given an array of numbers, and you're given a target value, let's say you're looking for number 1, you need to get index 0. So we're looping through a variable 0 to 9, and this is just pseudocode for for loop, and we don't use in range like in Python. We do if numbers num equals target, so we're checking if this is equivalent to the target given to us. We print the index, and what this code doesn't do is if the target isn't in the list, it doesn't print -1 or anything, just prints nothing. So if it's found, it's going to print the index. If it isn't found, it prints nothing. And you could probably figure out how you could print nothing, or print maybe a null value or -1 if it isn't in the list, maybe using some Boolean variables. You could track if it's found or not. And if it isn't found after this for loop, you can print that at the end. Maybe you can figure that out yourself, because I didn't feel the need to do that. You don't need to do that. Anyways, what are the benefits and drawbacks? So it can work on an unordered list, right? This list could be in any order because we're looping through each index. And it's very easy to implement. We need some basic selection, basic iteration. However, the negative is that its worst case time complexity is O of n, meaning that in the worst case scenario, we're going to have to loop through every single index in this list before we find our target, if the target is at the very, very end of the list. And this isn't a good thing. It's a much worse time complexity compared to the search we're about to cover, which is the binary search. So how does a binary search work? Well, it does have a prerequisite to work. The list needs to be sorted. But once it is sorted, it works by finding the midpoint of the list and then comparing it to the target value. Is it equal to, less than, or greater than the target? And based on this information, we can do different things, which we're going to see in the pseudocode in a second. And based on this information, you can repeatedly reduce the size of the list until you have a list of size 1 in the worst case scenario. This probably wouldn't happen a lot of times, where the new midpoint will equal the target. So what does that actually mean? What am I actually talking about here? So let's go over the pseudocode. And then again, we're going to go over some examples, some tracing, some past questions. Since we're repeatedly shortening the length of a list, a standard implementation uses recursion. However, if you were asked to write the program for binary search, they wouldn't actually expect you to do recursion. Obviously you can, but whenever they ask you to write a full program, they're very unlikely to ask you to do a recursive approach. They're more likely to do fill the gaps with recursion, or maybe doing a tracing algorithm. They want to make sure you understand how recursion works. They don't really test if you can implement a program in a recursive way, because it's quite difficult to do sometimes. They don't typically ask that. But since it can be implemented iteratively, they could be asked to write the program for a binary search. So here's the iterative approach, right? And how it works is we have an array of numbers, same as before, and we have a target, blah, 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 and this is the function. So it takes in numbers and the target node, and it establishes two variables. The first variable, which just tracks the first index, we can name anything, and then you have the last variable, which tracks the last index, where we're taking the length of numbers, which is 10, and we're minusing 1 to get the last index, because remember, we're counting from 0. So this index is 9, which is what last will track. And we have a while loop here. We're saying while first is less than or equal to last. And what this basically means is while this first index is before the last index, because as we reduce the size of the list and keep halving it, eventually this midpoint and us updating first and last will put first in front of last. And in that case, it's not on the list. The target node has not been found because it's not on the list. So we calculate the midpoint by doing first plus last div 2. There could be many ways to calculate midpoint. You could do first plus, last minus first, diff2, just anywhere you find the middle of a set, a middle of a list. There's many ways to do that. But you do integer division because you want an integer. And then we're doing a check. If numbers midpoint equals target, return midpoint. So we're saying if the midpoint index is equal to the target, we're returning it. However, if it's less than the target, so if the midpoint here is like 5 and the target is 8, 9, it's obviously less than the target. We're then going to push the first index forward. So the first index is now going to be 6 if our midpoint was 5. We've essentially cut off this half of the list. It's all gone because we're now only considering these numbers here. And then our else statement means that the midpoint is greater than the target. So 5 is greater than the target. Let's say our target is now 3. So what we're doing is we're setting last to be midpoint minus 1. If midpoint was 5, if midpoint's greater than the target, we only want to consider these indexes here. Index 1, 2, 3, 4. And we're discarding this whole rest of the list. Right? And we're repeatedly doing that until we find our target. Because if our midpoint is the target, we return the midpoint. And this midpoint calculation is going to keep getting updated as we change first and last. And while loop keeps going, this is going to keep changing until eventually we find our target. However, if we finish this while loop and we still haven't returned a value, the target isn't inside the list. So we return -1 to indicate that it's not on the list. We have to return something. It's a function. However, you could do this recursively, right? So let's go over the recursive approach. I will go over more recursion in my general programming video, which I will do at some point, because it is paper 2. A lot of paper 2 is just programming. But first, let's get through all the data structures and stuff. So, how does the recursive approach work? Now, it's very, very similar. We have our base case here, where we're just checking if first is less than or equal to last, which it should be if the target node is within the list. Not target node, the target value is within the list. And then we're doing very similar things. We're updating midpoint the same way. We're doing a similar check. However, we have our recursive calls. If it is less than target, we then do the exact same thing we did before, except we're changing first over here. We're setting first to be midpoint plus 1. So this is the same thing if we go back. You see how we update first to be midpoint plus 1? We're doing that here too, but except we're doing it within the recursive call. And this will then call binary search again, except with a new first value. And the same here, we're doing the exact same thing, but with a new last value, where it's equal to midpoint minus 1. And this will repeatedly call it until eventually we either find the midpoint because it's equal to the target, or it's not on the list and we return -1. The exact same thing. Now this might be a bit confusing if you don't really know how recursion works, but we're going to go over recursion a bit later on, so stay tuned for that. So, it has a worst case time complexity of log n, and I derived this in an earlier video on my TikTok, so if you're confused about that, you can check it out. And also when I cover Big O, I will go over this. Anyways, it's harder to implement than linear search. I feel like that's quite obvious. If we look at the code for linear search, it was what, 5 or 6 lines, and this one was what, 20, and the iteration's a bit more complicated, the selection's a bit more complicated. It's harder to implement. And this is something you can mention if you're asked in a written question. And the list has to be sorted. That is a prerequisite that has to be true. Yes, you could sort the list and then carry out a binary search, but the list has to be sorted before you can do the binary search. So let's go over some basic examples on how to perform these searches if it was asked in a trace. So we're given this list, 1, 2, 3, 4, 5, nice and simple, and we're asked to perform a linear search to find the target value 3. So the first thing we want to do is we want to compare index 0 to our target value. 1 doesn't equal 3, so we move on, we rewrite it, compare 2, 2 doesn't equal 3, we move on, we compare 3, which is the same as target value 3. So we found our value, nice and simple. We say 3 is equivalent to 3, found at index 2. We're very unlikely to ask how to trace a linear search. We're more likely to ask how to trace the sorting algorithms, but it is within the spec, so it's worth knowing. It's quite intuitive though, which is nice. So, can we do the same for a binary search? Well, we find the midpoint, and let's say our calculation ended up being 3, which it should do, and we say 3 is less than 5, so now we only need to check these 2 values. And then let's say our midpoint calculation ends up 4, because we're doing the same calculation each time. See, 4 is less than 5, so we discard 4, we have 5. It is the midpoint because it's the only value. 5 equals 5, found index 4. And as I mentioned, you aren't likely to be asked to trace a searching algorithm, but it's something we need to know. You're more likely to ask to trace a sorting algorithm, which we'll go over in our next video, but you do need to know how to do it. So, let's go over to GoodNotes and see what's going on. Okay. this is what we're asked to do. We're asked to explain how linear search would search an array for the index that stores clouds. So it will check index 0 to see if it equals clouds. If so, turns the index, right? As we mentioned earlier. But if not, what it will do is it will then increment itself, increment, and check next index until target found, or end of list, right? Or reaches the end of list. Say end of list. It's so hard to write on this trackpad. So let's go over to the mark scheme. Compare the first element to search item clouds. If it's equal to the search return index, nice, that's the first two confirmed. If it's not equal, move on to the next element. We don't even need to check the fourth bullet point because we've got those first three ones there. So why binary search cannot be used in this example? Well, let's check. Is this list sorted? No, because M should become before R if it was sorted. So you can just say not sorted and not sorted. See, nice and simple. Once you understand why these algorithms need to work and how they work, how they do, it's nice and simple. So let's look at this question here. And this is a skeleton question, which is probably the most likely way we're going to be asked to deal with the code for a binary search. Same with all of the other algorithms. It's more likely to be a skeleton, but some simple ones. And you could be asked for a binary search fully written the code, but it's unlikely. So let's see. Data array passes the parameter, the function returns index, search value within the array, and -1. So is search value as a parameter? Not yet. So we need to add search value in here. Search, right? And then we're updating middle. And if you see, we don't actually have any division yet. We also want to make sure it's integer division. So we do div2 to update our middle point. And then we have a check here. If upper bound is less than lower bound, then return -1. Yeah, because that means we no longer the data point is no longer within the list. And then we do if data array is middle is less than search value, lower bound equals middle 1, and upper bound equals middle -1. Else return middle. Because we've reached that midpoint, right? Let's see. Yeah, so we pass in search value, we do the integer division, return -1 if it's no longer in the list, we update middle, we update lower bound using the middle, and we update upper bound using the middle, and else we return middle. That's all done. Nicely done.